Here we look at using calorimetry to work out enthalpies of reaction in solution. The first example is a neutralization reaction, and we've got 50 centimetre cubed of 1 mole per decimetre HCl, and that's reacting with 45 centimetre cubed of 1.25 mole per decimetre sodium hydroxide. And through cooling curves, the maximum temperature rise was calculated to be 7.0 degrees. And we've got to calculate the enthalpy change for this reaction. First thing we do is calorimetry, so we use the equation Q is equal to mc delta T. Now, my mass in this case is the mass of the solutions that have been heated up, and we've got 50 centimetre cubed of HCl and 45 centimetre cubed of sodium hydroxide. We assume that the density of these solutions is equal to 1 gram per centimetre cubed, the same as water. Solutions are mainly water. So this 50 and 45 centimetre cubed, this 95 centimetre cubed in total, we assume then is 95 grams. My C is always 4.18, and that will always be given. My delta T is 7. That gives me 2779.7 joules. We now need to work out the delta H, which is obviously Q over moles. Now, this is a neutralization reaction, and usually we work it out per mole of water formed. But how many moles of water are we actually going to get? And in order to work that out, we need to work out what the limiting reagent is in this reaction. Is my limiting reagent HCl or is it NaOH? So we work out the moles of both the HCl and the NaOH. Moles of HCl, moles is equal to concentration times volume. And we've got 1 times 50 times 10 to the minus 3, and that gives me 0.05 moles. So that's the moles of HCl. Moles of NaOH, we work out in the same way. Moles is conc times vol, and it's 1.25 times 45 times 10 to the minus 3. And that gives me 0.05625 moles. So my limiting reagent is my HCl. So in effect, what we're saying is we've got 0.05 moles of this, 0.0625 moles of this. So the number of moles of water we're going to get is going to be the same as this. Because not all this is going to react, only 0.05 moles of that is going to react. This is in excess. So if we've got 0.05 moles of this, we'll form 0.05 moles of this. So that's the number of moles of water which is formed. So my delta H now is equal to my Q, which is 2779.7, divided by the moles of water which is formed, which is 0.0500. And that gives us 55,594 joules per mole of water formed. Again, this is a very, very big number. So you would divide this by 1,000. And that gives you 55.6 kilojoules per mole. But remember, it said that the temperature rose. And if the temperature rose, it was an exothermic reaction. So remember, we need to put a minus. So the actual final answer is minus 55.6, which is roughly what you get for a per mole of water formed in a neutralization reaction. We're now going to have a look at a second enthalpy of reaction in solution. But this time we're going to add a solid to a solution. It says there we've got 50 centimetre cubed of 1 mole per decimetre silver nitrate and 0.2 grams of zinc powder is added. The mixture stirred through cooling curves. The maximum temperature rise is worked out to be 4.3 degrees C. And we've got to calculate the enthalpy change per mole of zinc which reacts. First thing you do is, again, Q is equal to MC delta T. And Q then is equal to, now the mass is equal to 50 grams. Please be aware that you do not add the mass of the solid. That's a big no-no. So it's not 50.2, it's simply 50. So this is 50 times 4.18 times 4.3. And when you do that calculation, you get 899 joules. And we've got to work it out per mole of zinc that reacted. Now, we've got to work out again what the limiting reagent is, because for all we know, 0.2 grams of zinc, we might have had loads of that, might be in excess, we just don't know. So we've got to work out the moles of both. So we work out the moles of silver nitrate, and we do that, moles is conc times vol, so that's going to be equal to 0.1 times 50 times 10 to the minus 3, and that gives me 0.005 moles. So that's the number of moles of silver nitrate. We then work out the moles of zinc. And now we've got a solid, so moles is equal to mass over, because it's an element, AR in this case. So we've got 0.2 divided by 65.4. That gives me 0.00306 moles. Now, it might be tempting, to think, well, I've got a lower number of moles of zinc, therefore it must be the limiting reagent. However, we've now got to look at the equation. 2 moles of silver nitrate react with 1 mole of zinc. So in order for all this zinc to react, I've got to have 2 times this number of moles of zinc. So in reality, it's the silver nitrate which is the limiting reagent. And I'll say that again, because in order for all this zinc to react, all these 0.0306 moles to react, I would need this number times 2 for all that zinc to react. And I haven't got that. I've only got 0.005 moles of silver nitrate. In reality, of this 0.00306 moles of zinc, only half of this number is going to react. You're going to, in effect, get only 0.00250 moles of Zn reacts. So in reality, the zinc is in excess. And again, you can see that if we look at the equation. If you've got 0.005 moles of this, half that number of moles of zinc will react. So in reality, that's how many moles of zinc will react. So my delta H then is Q over moles. So my delta H now is 899, which is my Q, divided by 0.00250. When you do that, you get 35,960. Sorry, 35,000. 600 joules per mole. So what we need to do then is we need to convert that into kilojoules divide it by 1,000 to 3 significant figures, then that would give me 360 kilojoules per mole. But again, very important, we can see that the temperature rose, the temperature rise, so it's an exothermic reaction. So again, you need to put a minus in front of that. So that was a slightly more difficult calculation because, again, we've got to work out the limiting reagents in a reaction where we've got an equation which is not a one-to-one process. And that is enthalpies of reaction in solution.